Chapter 5.6 is going to be the graphs of the other 4 trigonometric functions. So we'll start with the graph of tangent. So we're not going to be doing any transformations with these. I just want to go over the properties and what the graphs look like. So for tangent, the period is not the same as the period as sine and cosine. The period is actually pi instead of 2 pi. So that means tangent of x would equal tangent of x plus n pi, meaning we could just keep on adding integer multiples of pi to x and they will end up giving us the same value. So it repeats itself every pi units. So the domain is going to be all real numbers except integer multiples of pi over 2. So if we remember what tangent equals with the quotient identity, it equals sine of x over cosine of x. So it's a fraction, so the denominator cannot equal 0. So that means the domain of all real numbers the domain is all real numbers except for when cosine, which is the denominator, equals 0. Cosine equals 0 at odd integer multiples of pi over 2. So that's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. The range of tangent is negative infinity to infinity. The x-intercepts are going to be when the numerator is equal to 0, which is integer multiples of pi. So that's pi, 2 pi, 3 pi, and so on. And the negatives also. And tangent is an odd function, meaning it's a 180-degree rotation of itself. And there are vertical asymptotes when that denominator is equal to 0. So if you remember back to rational functions and graphing rational functions, we had vertical asymptotes sometimes. So vertical asymptotes also appear here with tangent. So here is tangent of y equals tangent of x. So we can see the x-intercepts are integer multiples of pi. We can see that the asymptotes are odd integer multiples of pi over 2. And we have this shape that repeats itself over and over again for a period of pi radians. So usually when we think about how the curve looks for tangent, we think about it from negative pi over 2 to positive pi over 2, and that shape repeats itself over and over again. So even though it stops here on the edges, it's still going to keep on going and looking like this from negative infinity to positive infinity. Okay, for the next one, for cotangent. So for cotangent, it's important to know that this is the reciprocal of tangent, which is cosine of x over sine of x. So the period for this one is also going to be pi. The domain is going to be all real numbers except for when that denominator equals 0, which is when sine of x equals 0. So that's going to be integer multiples of pi. The range, negative infinity to infinity. The x-intercept is going to be when the numerator cosine of x is equal to 0, which are odd integer multiples of pi over 2. It is an odd function just like tangent, and there are vertical asymptotes when that denominator equals 0. So this is cotangent. So y equals cotangent of x. You can see what it looks like. It looks pretty similar in shape to tangent. We can see the x-intercepts at the odd integer multiples of pi over 2. We have the vertical asymptotes at integer multiples of pi, and we can see that one full cycle is a period of pi radians. Okay, so that shape's going to repeat itself over and over again from negative infinity to infinity. Next one for cosecant. So for cosecant, y equals cosecant of x. We have to remember that this is the reciprocal of sine. So this is actually going to help us graph it. So reciprocal functions have the same period. So this period is also 2 pi. The domain is going to be all real numbers except for when that denominator equals 0, which is sine of x. The range is going to be the exact opposite range as sine of x. The range of sine of x is -1 to 1. So the range of its reciprocal function is going to be everything else. Negative infinity to -1, union 1 to infinity. There are no x-intercepts because this will never equal 0. Oops, I just put y up here. I'm going to change that. And this is an odd function because sine is an odd function. And there's vertical asymptotes when that denominator equals 0. So when we're graphing this, it looks like a bunch of, it kind of looks like a bunch of parabolas actually, but they're not technically parabolas, but that's what it looks like. So we have these vertical asymptotes when sine equals 0. And what we have right here, we have sine of x actually graphed. So here's sine of x, this dotted line. You can use this to help you graph cosecant of x, because every time sine has a x-intercept, there's going to be a vertical asymptote for cosecant. And every time sine has a max value, cosecant's going to have a min value. And every time sine has a min value, cosecant is going to have a max value. So you can use that to help you graph these ones. And then you can see that one full cycle. I'll go from 0 to 2 pi. One full cycle is going to be a period of 2 pi radians. Okay, and then for the last one here, the graph of secant of x. So y equals secant of x, we have to remember that secant of x is the same as 1 over cosine of x because they are reciprocals. So reciprocals, just like I mentioned, have the same period. So cosine has a period of 2 pi, so does secant. The domain is going to be all real numbers except for when that denominator cosine is equal to 0, which are odd integer multiples of pi over 2. The range, once again, is going to be the exact opposite range as cosine, so it's going to be from -infinity to -1, union 1 to infinity. There's no x-intercepts because it'll never equal 0. This is an even function, just like cosine, and there's going to be vertical asymptotes when that denominator cosine is equal to 0. So this is what it looks like. It looks similar to cosecant, which we should expect. So if we graphed cosine, cosine would look something like this. And it's the same concept as sine compared to cosecant. Whenever cosine is equal to 0, we have a vertical asymptote. Whenever cosine has a max value, secant has a min value. Whenever cosine has a min value, secant has a max value for that specific interval. Okay, and then once again we can see the period here is a period of 2 pi radians for that little interval. It's going to repeat that over and over and over again from -infinity to +infinity. Okay, so definitely know these properties of these graphs and how to graph them, and that's it for this section.